There's a gap between two galaxies where nothing should be. No stars, no gas anyone had mapped, just 30 million light-years of empty black. And on one night, buried in a fresh batch of James Webb data, a single point of light sat right in the middle of it. At first, it was just 1 pixel brighter than its neighbors, easy to miss. But when the frames were lined up in order, that point had shifted, not flickered, not brightened, moved. Objects that far out aren't supposed to change position on a timescale we can watch. Galaxies drift across the sky over millions of years, far too slow for any single observing run to catch. This thing had crossed a measurable slice of that void between exposures taken days apart. The team pulled the raw files. They checked the pointing, the calibration, the detector for hot pixels that fake motion. Everything came back clean, and the dot was still there, still sitting in the dark where there was nothing to move around. The first read looked like an error, until a second instrument confirmed the exact same thing. So they lined up the exposures side by side and watched. Frame 1, the dot sits in a patch of empty sky, far from any galaxy edge. Frame 2, taken days later, the dot has slid. Not much, just a hair against the fixed stars behind it, but it moved. They stacked more frames on top of that. Each new image pinned the object a little further along the same line, like beads dropped one after another on an invisible thread. Nothing else in the field shifted. The background galaxies stayed exactly where they belonged, frozen the way distant things always are. That's the part that stops you. Out here, between the galaxies, there's supposed to be almost nothing to push against and nothing to see move. The gaps between galaxies run millions of light-years wide, mostly cold and empty. Yet this one point of light was crawling across that void, exposure after exposure, holding a straight and steady path. They had the direction. They had the frames. What they didn't have yet was the number that mattered. Then someone measured how far it had traveled, and the room went silent. Measuring motion in space isn't guesswork. You take 2 frames separated by a known amount of time, you line up the fixed stars behind them, and you check how far the target has shifted against that backdrop. The math is old, careful, and hard to argue with. So they ran it. They knew the exposure times down to the second. They knew the distance the object appeared to sit at. All that was left was to convert the shift into a speed. And the speed came back wrong. Not wrong like a typo, wrong like it broke the assumptions you build every other measurement on top of. For an object at that distance, the gap between frames meant it had crossed a stretch of space that nothing at that scale should cross in that window. Nobody in the room said the figure out loud right away. They just kept staring at it, waiting for the mistake to show itself. It didn't. Nothing natural was supposed to move like that. At least, that's what everyone thought. A careful team knows what to do next. They started tearing the data apart, looking for the lie. Cosmic rays were the first suspect, those high-energy particles that slam into a detector and leave bright false streaks that look like something's there when nothing is. But cosmic ray hits show up in a single exposure, then vanish. This thing persisted across separate frames taken hours apart, so they moved down the list. A satellite crossing the field, maybe, or a bit of space debris catching sunlight at the wrong moment. They pulled the orbital catalogs and checked every tracked object near that patch of sky. Nothing lined up. No known satellite, no rocket body, no piece of junk was anywhere close to that position at that time. Then came the boring explanations, the ones that usually solve these mysteries. A detector glitch, a calibration error, a stray reflection bouncing inside the instrument. They ran the checks twice, then a third time. Every test came back clean. The thing was real, it was out there, and it was moving. And the direction it was heading pointed somewhere no one wanted to consider. When they mapped the object's path across weeks of data, something about it stopped feeling random. It wasn't tumbling through empty space the way a stray rock would. It was threading a line, a narrow corridor that ran clean between the vast halos of dark matter wrapped around neighboring galaxies. Those halos are enormous, stretching hundreds of thousands of light-years past the visible edge of a galaxy. Anything drifting on a natural course should get nudged, bent, pulled off track by all that mass. This didn't. It held its line like the gravity around it had been accounted for in advance. The team ran the trajectory forward and back. Forward, it kept threading the gaps, avoiding the dense regions with a precision that read less like physics and more like intent. Backward, the line stayed just as clean, as if it had been traveling this exact route for a very long time. Nobody said the word out loud. You don't. Not in a room full of people trained to distrust their own instincts. But the path pointed somewhere, and once you saw where, you couldn't unsee it. This is where the story takes a turn nobody on the team expected. The room went quiet in a way that has weight to it. Not the silence of people waiting, but the silence of people who have run out of things to say. A dozen scientists, and none of them reached for a word. Someone leaned closer to the monitor, then leaned back. Another pulled up a second data set on the screen beside it, as if a fresh angle might turn the shape into something familiar. It didn't. The two readings agreed, and that was the problem. These are people who spend their careers second-guessing a flicker of light. They argue about decimal places. They build entire papers around ruling out the boring explanation. And here they sat, staring at something the boring explanations couldn't touch. Nobody said the name out loud, partly because saying it makes it real, and partly because no one was sure the name existed yet. What they had was a motion, a measurement, and a growing feeling that the sky had just handed them a question. To understand what they were looking at, you have to go back years before this night. Long before that room went quiet, there was nothing to point a telescope at. The idea started as sketches, arguments, and a single stubborn question about what we couldn't see. For decades, the deepest parts of the sky stayed dark, not because they were empty, but because our eyes weren't built for them. Ordinary telescopes catch visible light, the same range your own eyes use. But the faintest, oldest, and coldest things in the universe don't shine there. They glow in infrared, a kind of light that slips right past a normal mirror and never leaves a mark. So a group of engineers made a strange promise. They said they'd build an eye that could feel heat from across the universe, tuned to catch light that left its source before the Earth existed. On paper, it sounded closer to a wish than a plan. It would take 20 years, thousands of people, and a machine so delicate it couldn't be fully tested on the ground. And when it finally opened its eye, it saw exactly what it was designed to find, and something it wasn't. Because the reason Webb was even pointed there is stranger than the object itself. For most of the last century, we drew the universe as islands. Galaxies were the land, bright and full of stars, and everything between them was ocean. Empty water you'd never bother to map. That space is called the intergalactic medium, and the distances are almost cruel. The gap between the Milky Way and Andromeda runs about 2.5 million light-years. Between more distant galaxies, you're talking tens of millions of light-years of what we assumed was nearly nothing. So when the data showed something crossing that gap, moving through the dark where nothing was supposed to be, it broke the old picture. Not a star drifting inside a galaxy, something traveling between them, out in the water. And if something can move out there, then the void isn't a barrier, it's a road. That single idea rewrites what those enormous empty stretches actually are and what they might be carrying. But first, what did we believe about that emptiness before Webb looked? Picture the space between galaxies, not the tidy gap you imagine, but a gulf so wide light takes millions of years to cross it. For most of a century, that's where the story of the universe simply stopped. Astronomers had a name for it, the intergalactic medium, and a reputation to match. A near-perfect vacuum, roughly 1 atom per cubic meter in the emptiest stretches, colder than almost anywhere else, and dark in every direction you point. Compare that to the air in front of you, packed with something like 25 quintillion molecules in that same cubic meter. The void wasn't just empty, it was the definition of empty, the dead zone we used to measure everything else against. So the textbooks drew a clean line. Galaxies were where things happened. The gaps between them were leftover space, cosmic filler, the parts of the map you skipped past to get to somewhere interesting. Nothing lived there, nothing moved there, nothing to see. That belief held for a century, until one telescope quietly broke it. To understand how a telescope caught something drifting through the dark between galaxies, we have to go back, long before it ever launched. Back to a time when the tools we had could barely see the edges of what we wanted to know. In the 1980s, astronomers were pushing Hubble toward the sky, and even then, a handful of people were already looking past it. They knew visible light had a ceiling. The oldest, faintest objects in the universe weren't glowing in colors our eyes could catch. They were hiding in infrared, stretched and reddened by billions of years of travel. So a question started circulating in quiet meeting rooms and hand-drawn proposals. What if we built something that could see heat instead of light? Something that could stare into the cold and pull the first galaxies out of the black? It sounded impossible. The mirror would need to be enormous. The instrument would have to run colder than almost anywhere in the solar system. And it starts with a dream almost everyone said was too expensive to survive. Back in 1989, before Hubble had even reached orbit, a room full of astronomers sat down and asked a stubborn question. If Hubble could see far, what would it take to see almost to the beginning? The answer scared the accountants. You'd need a mirror far bigger than anything ever flown, wide enough to gather light that had been traveling for over 13 billion years. Hubble carried a mirror 2.4 meters across. That was already a marvel lofted into space. But to catch the faint infrared glow of the earliest galaxies, engineers sketched something closer to 6.5 meters, nearly 3 times wider, with more than 6 times the light-gathering area. A single piece of glass that size could never launch, so the idea shifted to something stranger. A mirror built from smaller segments that would unfold in the dark like a flower opening. 18 pieces, each one hexagonal, each one coated in a whisper-thin layer of gold. It was a beautiful sketch on paper in those early years. Nobody knew that one design choice would later matter more than any other. So why hexagons? A round mirror would have worked, but hexagons tile together with almost no gaps between them. Pack 18 of them edge to edge, and you get one nearly continuous surface, 6.5 meters across, with none of the wasted space a grid of squares or circles would leave behind. That shape also folded. A single mirror that size could never fit inside a rocket, so the segments were arranged in 3 wings that tucked in for launch and swung open in space. The geometry wasn't just elegant, it was the only way to get an eye that big off the ground. Then, the gold. Aluminum reflects visible light just fine, but Webb was hunting infrared, and gold reflects infrared far better, bouncing back around 98% of it. The coating is only about 100 nanometers thick, a few hundred atoms, spread across roughly 25 square meters of glass-smooth beryllium. Every choice pointed the same direction. More collecting area, cleaner reflection, less light lost. That mirror was built to see the faintest things, and faint was the whole point. Here's the strange part about looking deep into space. The farther away something is, the more its light stretches on the way to us. The universe has been expanding for 13.8 billion years, and that expansion tugs on every wave of light crossing it. A galaxy that first glowed in visible light doesn't reach us that way anymore. By the time its light has traveled billions of years, those waves have been dragged out, stretched long, shifted all the way past red and into the infrared. To catch the oldest light, you have to look in a color your eyes can't see. Infrared has another gift. It slips through dust that stops visible light cold. Stars being born inside thick clouds, cores wrapped in haze, cold gas drifting in the dark. All of it hides from ordinary telescopes and glows plainly in infrared. That's why Webb was tuned to heat instead of color, built to read the faintest warmth from the edge of time. Infrared can reveal what visible light hides, including things that were never meant to be found. So Webb doesn't circle the Earth like Hubble does. It sits about 1 million miles out, at a spot called L2, where the pull of the Sun and the Earth balance just enough to let it hang there quietly. From that distance, our planet is a pale dot behind it, and the telescope keeps its back to the Sun, the Earth, and the Moon all at once. That arrangement matters more than it sounds. A tennis court-sized sun shield blocks the heat from all three, so the mirror can drift down to around -370 degrees Fahrenheit. It has to be that cold, because Webb reads warmth, and any heat of its own would drown out the faint signals it's hunting for. Day after day it runs through its schedule. It swings toward one target, holds steady, collects light for hours, then moves to the next. No astronaut has ever touched it out there. It just works in the dark, sending its data back across that million miles a few times a day. There's no weather at L2, no city glow, no atmosphere smearing the view. Out there, with nothing around it, Webb had a perfect view of the nothing between galaxies. So the work began, the way it always does. Point the telescope at a patch of sky that looks like almost nothing, then hold still and let the photons trickle in. Some of that light left its galaxy more than 13 billion years ago, back when the universe was a few 100 million years old. Webb's first deep field landed in July 2022, a slice of sky about the size of a grain of sand held at arm's length. In that tiny square sat thousands of galaxies, some so far away their light had been stretched clean out of the visible range. It was the kind of picture astronomers had waited their whole careers to see. After that came the surveys. Night after night, frame after frame, the same patient routine that built our maps of the early cosmos. Nobody expected fireworks from a survey field. You take the data, you calibrate it, you file it, and you move on to the next pointing. That's the job. One of those routine frames would turn out to be anything but routine. Zoom out far enough and the galaxies start to look like decoration. Between the bright clusters sit the voids, enormous stretches of near nothing that make up most of the volume of the universe. A single one can span 100 million light-years or more, and inside it, the matter density drops to a fraction of the cosmic average. These aren't small gaps. If you drop the Milky Way into the center of a typical void, its nearest big neighbor could be tens of millions of light-years away in every direction. Light that enters that emptiness travels for ages before it touches anything again. That's what makes the voids so hard to study. There's almost no gas to glow, almost no dust to catch starlight, almost nothing to reflect a signal back to us. Whatever moves through that space moves in the dark, unlit and unannounced, leaving no obvious trace on the instruments pointed its way. So the voids became a kind of blind spot, mapped by their edges and assumed to be barren in the middle. For decades, scientists assumed nothing could survive a journey across that dark. But the gaps between galaxies aren't truly empty. Stretch a hand across a cubic meter of that space, and you'd sweep up fewer than one atom on average, mostly hydrogen left over from the early universe. Compare that to the air you're breathing right now, which packs about 25 quintillion molecules into the same volume. The difference is almost impossible to picture. Astronomers call this thin haze the intergalactic medium, and it holds more ordinary matter than every star and galaxy combined. It's just spread so thin that light passes through it mostly untouched. You can't see it directly. You infer it from the faint shadows it casts on the light of distant quasars behind it. So the picture settled into something quiet, a few stray atoms drifting in the cold, nothing dense enough to catch, nothing bright enough to notice. The kind of place where you'd expect a signal to fade out and disappear for good. And for a long time, that assumption held. Almost nothing, it turns out, is not the same as nothing at all. So in mid-2022, once Webb finished its commissioning checks, the real science calendar kicked in. Time on this telescope gets rationed out in blocks, and a committee argues over every hour, because there's never enough to go around. One of the first approved programs was a deep survey of a patch of sky that looked, frankly, boring. The plan was straightforward. Point the near-infrared camera at a region between two well-mapped galaxy clusters, hold steady, and stack exposure after exposure to pull faint light out of the dark. The goal was distant galaxies, the oldest ones, the smudges of red that had been traveling toward us for 13 billion years. To catch light that old and that dim, you don't take one photo, you take dozens, sometimes over several hours, and let them pile up until patterns emerge from the noise. It's patient work, and nobody expected surprises. That's the point of a survey. You look at the same quiet spot again and again and trust the data to reward the repetition. The team had a target in mind, and it wasn't the thing they'd end up famous for. The assignment was a cluster of distant galaxies, faint smudges of red light that had been on the schedule for months. These were old systems, some of them shining from more than 10 billion years ago, back when the universe was barely a third of its current age. The team wanted their shapes, their colors, the slow drift of their star formation. It was patient work, the kind that doesn't make headlines. You point the telescope, you wait, you gather photons that left home before the sun existed. Night after night, the same coordinates, the same handful of galaxies, filling in a picture the astronomers had been sketching in their heads for years. Those galaxies had names, catalog numbers, whole careers built around understanding them. Everyone knew the plan, and the plan was good. It was the kind of steady, unglamorous science that fills observatory logs and quietly rewrites textbooks a decade later. And that was supposed to be the story. The galaxies were the subject, the reason for every second of exposure time. Right beside their intended subject, something else had wandered into the frame. But before any of that, there were just the nights. Webb doesn't work like an old backyard telescope where you point and look. Every observation gets scheduled weeks ahead, slotted into a queue that runs around the clock, 1.5 million kilometers from Earth. For this program, the routine was simple. Point at the target field, hold steady, let the near-infrared camera soak up photons for hundreds of seconds at a time, then do it again and again. Between exposures came the unglamorous work that keeps the whole thing honest. Dark frames to measure the detector's own electronic noise, flat fields to map how each pixel responds to light, calibration shots that no one ever frames on a wall, but without them, the science falls apart. Night after night, the frames came down clean, star positions checked out, background levels sat right where they should, nothing flagged, nothing flashing red, nothing that made anyone lean closer to a screen. It was, by every measure the team had, a textbook run. The data looked perfectly normal, which is exactly why it took so long to notice. The frame in question came in during a scheduled exposure, roughly 1,000 seconds of the detector just sitting open, drinking in whatever light had traveled billions of years to reach it. Webb's instruments don't blink. They collect photon after photon, stacking them into a picture that no human eye could ever see on its own. And somewhere in that long, patient stare, a single point of light landed on the sensor. It wasn't bright, it wasn't strange, at least not in any way the automated systems were built to catch. It was a smudge of infrared sitting exactly where nothing was supposed to sit. The exposure finished, the data compressed, and the frame slid into the archive alongside dozens of others taken that same night. No alarm, no note, no reason for anyone to circle back to it. The telescope had done its job flawlessly, recording something it had no idea it was recording. That frame would eventually change everything, but not yet, not for weeks. At the time, it was just one faint dot among thousands. Picture the frame the way the sensor recorded it. Thousands of galaxies, some spiral, some smeared into faint orange ovals, packed edge to edge across a patch of sky smaller than a grain of sand held at arm's length. Buried in all that, near the lower quadrant, sits a single point of light, maybe a few pixels wide. Nothing about it stands out. It's dimmer than the galaxies around it, roughly magnitude 27, right at the edge of what Webb's NIRCam can pull from the dark. If you scrolled past it, and people did, your eye would read it as just another distant smudge. There's no arrow pointing to it, no color that screams for attention. In a field this crowded, a faint dot is the most forgettable thing there is, one of maybe 20,000 sources flagged automatically by the pipeline that night. So it sat there, catalogued and ignored, a number in a table nobody had reason to question. The image got archived, the team moved on to brighter, easier targets, and the timing of when someone finally looked twice? Almost too perfect. Her name was Dr. Elena Vasquez, and by 2023 she'd been staring at telescope data for the better part of 15 years. She started back in grad school, hunched over old Hubble frames, learning to tell a real signal from a smudge on the sensor. The work hadn't changed much. The pixels just got sharper. She wasn't part of the headline teams, the ones chasing the earliest galaxies or the exoplanet atmospheres that made the press releases. Elena did the quiet work, the calibration passes, the second look at frames everyone else had already filed away. "Somebody has to check the leftovers," she used to say. On the night this began, she wasn't even supposed to be working. A backlog of survey images had piled up, thousands of them, and she liked clearing the queue when the lab was empty and the coffee was bad. One frame after another, flagging cosmic rays, marking dead pixels, the same motions her hands had made 10,000 times. Then one image loaded, and something in the corner of it caught her eye. She almost deleted the frame as noise, and then she stopped. Years earlier, when she was still new to this, a supervisor told her something that stuck. The pipeline is only as smart as the person watching it, so she built a small ritual for herself, nothing fancy, nothing in any manual. Whenever a frame felt slightly off, she'd pull up the previous exposure of the same patch of sky and set them beside each other. 2 windows, edge to edge, same coordinates, same scale. Then she'd flick her eyes back and forth between them, left, right, like she was proofreading 2 nearly identical pages. Most of the time it turned up nothing. A speck of dust on a detector, a hot pixel that had been misbehaving for weeks, the kind of thing you learn to ignore after a few hundred nights. But the human eye is stubbornly good at one specific job. It notices when a thing that should sit still doesn't. Software checks brightness and shape against a threshold. Her eyes checked position against memory. So she did what she always did. She opened the earlier frame, dragged it alongside, and lined the 2 up. That one habit was about to catch something no automated system had flagged. The 2 frames sat there, taken 4 nights apart, pointed at the same patch of sky, same coordinates, same instrument, same filter. When you stack exposures like that, they're supposed to be twins. Every star, every smudge of a distant galaxy, locked in the exact same spot. That's the whole point of comparing them. The sky, at these distances, doesn't change on a human timescale. A galaxy 10 billion light-years out isn't going to shift in your lifetime, let alone in 96 hours. So you overlay the images, and everything should line up down to the pixel. She scrolled across the top edge, checking. The bright foreground stars matched. The faint background galaxies matched, each one a frozen little smear exactly where it belonged. Frame A, frame B, indistinguishable. She started to relax, the way you do when the boring answer is winning. Then she reached the lower left quadrant where that single faint dot had caught her eye earlier. She flicked between the 2 exposures, back and forth, waiting for it to sit still like everything else. But one dot wasn't where it had been. She stopped flicking and just stared. On the first exposure, the dot sat maybe a pixel or 2 to the right of a faint background smudge. On the second, taken barely an hour later, it had slid to the left of it. That shouldn't happen. Stars don't move on human timescales. Galaxies don't move at all. Not in a night, not in a lifetime, not in a way any telescope could catch between 2 frames. Everything else in that field was locked in place, exactly where physics said it should be. The same anchor points, the same alignment, the same pattern repeated across both images. Only this one speck had shifted, cleanly, in the same field, under the same instrument, in the same pointing. She measured the gap with her cursor, then measured it again. The offset was small, but it was real, and it was consistent. Something in that frame had changed position, while Webb held perfectly still. Her first thought was a mistake. Her second thought was worse. So she did what any careful analyst does. She threw the result out and started over. New reference stars, fresh calibration, the alignment run from scratch on raw frames straight off the archive. If the shift was a processing slip, this would erase it. A bad flat field, a rounding error in the astrometric solution, a single hot pixel nudging the centroid. Any of those would vanish the moment she rebuilt the math from clean inputs. She matched 40 background stars across both exposures, every one of them locked into place, sub-pixel, exactly where it should be. The grid held. The telescope pointing checked out. Nothing in the field had drifted, nothing was smeared. Except that one dot. It sat a fraction off from where it was hours earlier. Same as before, same direction, same tiny step. She ran it a third time, then a fourth, changing the method each pass to catch her own bias. The number wouldn't move, or rather, the dot kept moving and everything anchoring it stayed nailed down. Then she pulled a third frame from later that night. The dot moved again, and the pattern was too straight to be an accident. So she did nothing loud, no message to the group chat, no flag raised in the shared log, no note pinned to the dataset where anyone scanning it might stumble across her hunch. She just kept pulling frames. Frame 4 came from a different exposure block, taken hours apart. Frame 5 sat in a folder someone else had already signed off on as clean. Each one she opened alone, at her own desk, measuring the same faint smudge against the same fixed background stars. She logged the coordinates by hand in a private file, pixel by pixel, timestamp by timestamp, building a track nobody else could see yet. If she was wrong, it stayed her mistake, quiet and contained. And if she was right, she wanted the case airtight before a single skeptical colleague got a chance to wave it off as noise. So the full picture stayed hidden, growing in one notebook on one screen, while the rest of the team worked the data blind to what she'd found. When she finally spoke up, the entire project changed direction overnight. The email went out at 2 in the morning, subject line blunt, 3 attachments, no speculation in the body. She'd stripped out every guess and left only the measurements, the frames, the offset in pixels between one exposure and the next. If someone was going to argue, she wanted them arguing with numbers, not with her. By the time the team lead opened it over coffee, she'd already fielded 2 replies asking if the timestamps were real. They were. Within the hour, a group chat spun up, then a call, then a shared folder with everyone's initials on it. People who'd been quietly working separate corners of the survey suddenly pivoted onto the same faint dot. Telescope time got reshuffled. Someone pulled archival images nobody had bothered to check in years, hunting for the object in older data. Nobody was calling it anything yet. That was the rule they set fast, out loud, before excitement could run ahead of the evidence. Their first job was to prove it wasn't something boring, and that got hard fast. So they started crossing things off, one boring possibility at a time. First up, an asteroid. Rocks in the main belt move at a predictable clip, and their brightness holds a certain signature. This dot didn't match the motion, and it didn't match the light. Next, a comet. Comets give themselves away with a coma, that fuzzy halo of gas and dust that swells as they warm. There was no coma here. No tail, no outgassing, no smear of ice boiling off. Just a hard little point that refused to blur. Then the satellites. There are thousands of tracked objects in orbit, and every one of them has a logged path you can check against a timestamp. They pulled the catalogs and matched the coordinates. Nothing known was sitting where this thing sat. One by one, the safe answers ran out. Asteroid, gone. Comet, gone. Satellite, gone. Every explanation they trusted, the kind you reach for precisely because it's dull and reassuring, quietly stopped working. Every ordinary explanation fell apart. Therefore, they had to consider the extraordinary. So they went after the most obvious survivor first, an asteroid, something drifting through our own solar system, close enough to smear across a frame while the stars behind it held still. But an asteroid gives itself away fast. It moves at a specific pace against the background, and it sits at a specific range, tens of millions of kilometers out at most. You can check both. They did. The math came back wrong in a way that didn't leave room for argument. Whatever this was, it wasn't parked in the neighborhood between Mars and Jupiter, and it wasn't creeping along at rock belt speeds. The numbers pointed outward, way outward. An asteroid you can catch and time and pin to an orbit. This thing refused every box they tried to fit it in. It was moving too much, and it was reading too far, and those two facts pulled in opposite directions unless you accepted where it actually sat. The distance alone put it somewhere no rock has any business being. So they nailed down the distance, and it wasn't close, not the edge of our galaxy, not the halo of old stars that drifts out past the spiral arms. It sat beyond all of that, in the open dark between galaxies, where the star count drops to almost nothing per cubic light year. That's the part that made the room go quiet. The space between galaxies isn't a highway. It's the emptiest real estate in existence, millions of light years of nearly perfect vacuum. And things don't just wander out there. Stars are born inside galaxies. They live and die inside galaxies. This object was parked in the gap. They ran the parallax and the photometry again, tightened the error bars, and the answer held, firmly outside, genuinely intergalactic. Nothing about the position could be explained away by a bad pixel or a foreground smudge. And they still hadn't looked hard at the speed. That measurement was sitting right there in the data, waiting, and they kept it boxed up a little longer, because distance changes what speed means. A number that sounds calm up close turns monstrous once you know how far you're really seeing. And once they knew how far, the speed number became terrifying. So they ran the conversion, distance times angular motion, and watched the figure resolve on the screen. The object wasn't drifting. It was tearing across space at a velocity that would cross the gap between Earth and the Moon in seconds. Most stars in a galaxy move at a couple hundred kilometers per second, held in a slow orbit by all the mass around them. This thing was moving several times faster than that, well past the point where a galaxy's gravity can hold anything down. That's the number that made the room go quiet. Past a certain speed, an object isn't circling anything, it's leaving, and nothing local is strong enough to reel it back in. Natural objects don't just wake up one morning going that fast. There's no gentle process that nudges a body up to a speed like that over time. Velocity that extreme has to come from a single violent event, one enormous shove in the deep past. So the question stopped being what is it, and became what happened to it. Something had to have thrown it, and only a few things in the universe can throw that hard. Start with the biggest hammer we know of. A supermassive black hole sitting at a galaxy's core can grab a passing binary star, swallow one, and fling the other outward at over 1,000 kilometers per second. We call those hypervelocity stars, and they're the fastest natural projectiles anyone has ever clocked. Then there's the supernova slingshot. Two stars orbit each other tight and fast. One detonates, and the explosion snaps the gravitational leash. Whatever was left goes tearing off in a straight line at whatever speed it was already orbiting, sometimes hundreds of kilometers per second, with nothing left to pull it back. A few can even come from three-body chaos, stars swinging so close that one gets ejected while the other two pair off. Every one of these needs the same thing, though: a dense, crowded, violent place, a galactic center, a stellar nursery, somewhere packed tight enough for gravity to do real damage. So the astronomers had a short list of suspects, and each one leaves a return address. Follow the path back, and you should land in a busy neighborhood. But when they traced the object backward, it didn't come from where any of those live. So they did what any careful team does. They took the object's measured velocity, its position across 3 separate nights, and they ran the clock backward. Not by hours or days, but by tens of thousands of years, watching the projected path stretch out behind it like a thread pulled through the dark. The math here isn't guesswork. Every point they'd recorded fed into the same trajectory, and the trajectory only pointed one way. You give a moving object a speed and a direction, and geometry tells you where it's been. There's no room to fudge it. They expected the thread to snag on something. A dense star cluster, the churned-up core of a galaxy, the wreckage of a collision, anywhere with enough mass to fling a body out at the speed they were seeing. Instead, the line ran clean. It slipped past every candidate they'd flagged, past the crowded regions, past the obvious gravitational engines, and kept going into open space. The line led into a patch of sky that should have been completely empty. So they zoomed in on that patch, Deeper exposures, longer stares, the kind of imaging that pulls faint objects out of the dark. They expected something to surface, a dim galaxy, a smear of old stars, anything with enough mass to fling an object outward. Nothing came up. The field stayed black across the wavelengths Webb is built to see, from the near-infrared out to about 28 microns. No cluster, no dwarf companion, no gravitational anchor sitting where the trajectory said one had to be. And this wasn't a small gap. Backtracking the motion put the origin point tens of millions of light-years from the nearest known galaxy, deep inside a cosmic void where matter thins out to almost nothing. Regions like that are the emptiest places we've ever mapped. Which left the team staring at a contradiction. Something moving that fast needs a launcher, a heavy object to slingshot it, and there was no launcher anywhere in frame. The math wanted a source, and the sky refused to give one. A thing launched from nothing shouldn't exist, at least, that's what the models insisted. So the team did what astronomers do when the sky won't cooperate. They ran it as a simulation, feeding in the object's mass, its trajectory, and that stubborn velocity, then asked the computer to build a plausible origin. The runs came back empty, over and over. You can't get a body moving that fast without something massive doing the throwing, and every model that tried to skip the launcher just fell apart. Give it too little mass nearby, and the numbers refused to add up. Give it enough, and that mass should be glowing, right there in the frame, bright enough to spot. They tuned the parameters for days. A rogue star here, a hidden black hole there. Each scenario either produced a launcher too bright to hide or a slingshot too weak to matter. The object sat in the data like a contradiction, real and impossible at the same time. What could throw a thing this hard should be one of the loudest objects in the neighborhood, not a blank patch of sky. And that gap between what the math demanded and what the images showed kept growing. So they widened the search and found the void wasn't as empty as the maps claimed. When they stacked the deep field frames, layering exposure on exposure, a faint irregularity crept out of the noise, right where the object's path traced back. It wasn't a star. It wasn't a galaxy anyone had logged. It sat in that supposedly empty corridor, like a smudge someone forgot to erase. At first, the team assumed it was an artifact, a stray glint bouncing through the optics, the kind of ghost that shows up when light scatters inside the instrument. So they reprocessed the data with a different pipeline, then a third. The shape held. It stayed put across separate observations, which is exactly what a real object does, and a glitch never can. So now there were two mysteries stacked on top of each other. Something had been flung across the void at a speed the models couldn't explain, and it seemed to have come from a spot that wasn't actually vacant. A structure was sitting there, dim and unaccounted for, quietly bending the story into a new shape. Whatever was hiding there had been invisible to every telescope before Webb. So the team went looking. They pointed Webb back along the object's trail, the exact line it had traveled before it started moving toward us, and they let the detector sit there and collect light for a long stretch. At first, nothing. Just the grainy black you'd expect from a patch of empty sky. Then, as the exposure stacked up, something began to surface. A glow so faint it barely cleared the noise floor, sitting right where the back trail pointed. It wasn't a star. Stars read as sharp points of light, single pixels burning clean. This was spread out, soft at the edges, more like a stain on the image than a source. The kind of thing you'd normally write off as a flaw in the sensor. But it didn't move when they retook the frames, and it didn't fade. It stayed put, exactly on the line, glowing at a level that no earlier instrument could have pulled from that darkness. Webb was seeing something that had always been there, waiting. And once they had enough light to trace its outline, one detail stopped them cold. The smudge had a shape, and the shape didn't match anything in the catalogs. So they did what any careful team does. They pulled up the big surveys, the ones that have mapped this patch of sky for decades. The Sloan Digital Sky Survey, the Pan-STARRS Archive, the old Hubble Deep Fields. If this thing had been seen before, its coordinates should light up a match. Nothing came back, No entry, no catalog number, no faint prior detection sitting in someone's data waiting for a second look. The position where Webb found its glow was, on paper, empty sky. That's the part that's hard to sit with. We've catalogued billions of objects, tagged them, measured them, filed them away by brightness and color and distance, and here was a structure bright enough for Webb to resolve, close enough to matter, and it lived in none of those files. So the usual next step, comparing it to known types, checking which family it belonged to, didn't work. There was no family to check against. To even describe it, the team had to invent new questions. So they did what any group does when one person can't hold every thread at once. They split. 3 small teams, each chasing a single piece of the puzzle, working in parallel so nobody got lost in someone else's dead end. The first team took origin. Where did this thing start, and what path did it trace to end up drifting between galaxies? The second team took speed, measuring the motion frame by frame, trying to pin down exactly how fast it was really traveling and in which direction. The third team took composition. What is it actually made of? That question sounds simple until you're staring at a spectrum that doesn't match anything in the reference files. And here's what made those weeks strange. Each team was told to hold their findings until all 3 finished. No comparing notes, no early hints, no letting one result color another. They wanted clean, independent answers before anyone tried to fit the pieces together. The composition team came back first, and their result made no sense. When you split an object's light into a spectrum, each element writes its own signature. Dark lines where atoms absorb, bright lines where they emit. It's a fingerprint, and it doesn't lie. The team fed the object's light through that process, expecting something ordinary. What came back was heavy metals sitting right next to signatures you'd only see in gas that's barely cooled since the early universe. Iron and nickel, the kind forged inside dying stars, layered against light hydrogen and helium ratios that point to something ancient and untouched. Those 2 stories don't belong in the same object. One says this thing was cooked in stellar furnaces and enriched over billions of years. The other says it's pristine, formed before generations of stars had time to salt the cosmos with heavier elements. Both readings held up when they checked the calibration twice. They ran it again with tighter error bars, expecting one signal to fade. Neither did. The numbers just sat there, stubborn and clear. The elements they saw shouldn't coexist in a single moving body. Start with the light itself. When you split it apart, a spectrum reads like a fingerprint, each dark line marking an element that absorbed a specific slice of the glow. Usually, those lines tell a clean story. One temperature, one history, one kind of object. This spectrum didn't. There were signatures you'd expect from a hot, young stellar body, sharp hydrogen and helium features burning through the near-infrared. Right beside them sat heavier stuff, carbon and silicate dust, the kind of material that takes generations of dying stars to build up. Those 2 things don't share an address. One says fresh, the other says ancient. Mixing them in a single object is like finding a newborn's cry recorded on a wax cylinder from a century ago. The team ran the calibration again, checked for contamination, for a background source bleeding into the frame. Everything held. The lines stayed exactly where they were, refusing to resolve into anything familiar. So they stopped trying to force it into a category and just listed what the data insisted on. And one reading suggested the object was far older than its surroundings. The age numbers came from the light itself. Old stars burn cool and red, stripped of the heavier elements that later generations inherit, and this object carried that same starved signature. When they modeled it, the fits kept sliding toward the deep past, well past 13 billion years. That put it among the first structures to ever light up, the generation that formed when the universe was barely a few 100 million years old. Everything nearby had been recycled a dozen times since then, seeded with carbon and oxygen and iron from countless dead stars. This thing looked like it had missed all of it, frozen in the composition of an era that should have vanished long ago. Nobody said out loud what that meant. The estimate sat in the spreadsheet next to the others, one line among many, and they moved on to check it again. But the implication was already there, waiting, and it wouldn't stay quiet for long. If it was that old, it had been traveling for almost the entire age of the cosmos. Think about what that distance really means. Light itself, moving at 300,000 kilometers per second, needs billions of years just to cross the gaps this object may have wandered. It didn't take any shortcut. It plodded through emptiness so vast that whole galaxies drifted apart while it moved. When it set out, the universe was a younger place. The first stars had only recently switched on, galaxies were still clumping together, and the elements we're built from were barely starting to spread. Something began a journey back then, and it kept going while all of that unfolded around it. You can't picture a path that long in one image. The scale slips through your fingers. Every marker the team could reach for, redshift, brightness, spectral lines, pointed at a traveler that had been in motion for nearly the entire history of everything. And where it was headed stayed hidden. No terminus, no clean answer for the destination, just a trajectory stretching out past anything they could measure. And it was still moving, which meant its story wasn't finished. So they went back for another look. Webb slewed to the same patch of sky, weeks after the first detection, and the team fed in the exact coordinates their model had spit out. If the object was real and moving the way they thought, it should sit right there, nudged along its line by a predictable amount. And it did. The faint smudge showed up almost dead center in the predicted window, shifted along the same track, at the same pace, no wobble, no correction needed. One pass could be a fluke. Two passes lining up like that starts to feel like something else. They ran a third, then a fourth, spacing them out to stretch the baseline and squeeze the error bars tighter. Every time, the thing landed where the math said it would, marching along that same stretched-out trajectory toward wherever it was going. Nobody was talking about the destination yet. That part still ran off the edge of everything they could measure, so they held it and kept their eyes on the motion instead. The prediction held perfectly, therefore the team started to trust the impossible numbers. So they ran it again. Same object, fresh exposures, different nights, and the position landed exactly where the math said it would, down to a fraction of a pixel. When something obeys your predictions that cleanly, you stop treating it like an error and start treating it like a fact. The measurements tightened with every pass. Its motion across the sky came in at a steady, repeatable value, small but real, the kind of drift you only catch when you stack weeks of data and let the numbers settle. Nothing in the sensor noise wandered like that. Nothing random holds a line. They cross-checked the calibration against known stars in the same frames, and those anchors sat still, right where they belonged. Only this one point kept walking. That killed the easy explanations, the smudges, the glitches, the hopeful mistakes people reach for first. By now, the confidence wasn't a feeling anymore. It was a curve on a plot, narrow and stubborn, closing in on a thing they still couldn't fully name. The what stayed just out of reach, even as the where got sharper by the day. With trust came a harder question nobody wanted to ask out loud. The question was simple to say and heavy to hold. Is this a natural object, or is it something else? Nobody wrote it on a slide. Nobody said it in the meeting. You could feel it in the way people phrased their emails, hedging, circling, reaching for words like anomaly and unexpected, instead of the words sitting underneath. A cold thing crossing empty space between galaxies, holding its shape, keeping its pace. Rock does that. Ice does that. But so do other things, if you let your mind wander where scientists are trained not to. So they didn't answer. That was the discipline of it. You don't get to skip to the ending you want, or the ending you fear. You sit with the data, and you refuse to name it until the numbers force your hand. And the numbers weren't forcing anything yet. Every measurement they had could fit a dozen ordinary explanations, and ordinary was where the work had to start. To rule out the unthinkable, they first had to rule in every natural possibility. So they lined the suspects up, one by one. First candidate, a rogue star, kicked out of its galaxy by a gravitational slingshot. Those exist. We've clocked a handful screaming through the Milky Way at over 1,000 kilometers per second. But a rogue star burns bright, and this thing barely registered in visible light. Next up, a primordial remnant, something left over from the first few minutes after the Big Bang, a clump of ancient matter that never became a proper star. That fit the age, and it fit the weird chemistry. It did not fit the way the object held together, too dense in one reading, too loose in the next. Then the strange one, exotic matter, the kind physicists write on chalkboards but rarely expect to photograph. A body made of something that doesn't behave like ordinary gas or dust. It could explain the motion. It couldn't explain the light. Every model got them close. Every model broke on the next data point. Each candidate explained one clue and contradicted another. So start with the simplest answer on the table. A rogue star, one of the roughly 1,000 hypervelocity stars our galaxy is thought to fling outward, kicked loose when a binary partner strays too close to the black hole at the center. One star gets swallowed, the other gets launched at speeds over 1,000 kilometers per second. On paper, that fit the motion almost perfectly. But a slingshot like that leaves fingerprints. A star born near a galactic core carries a specific chemical signature, heavy with metals forged in dense, crowded stellar nurseries. This object had almost none. The spectrum read like something assembled somewhere ancient and empty, nowhere near the machinery that would have thrown it. And the timing refused to cooperate. A hypervelocity star that old, moving that fast, should have burned through its fuel and gone dark billions of years into the trip. The math kept pointing back to an age that didn't match a living thing, a star that lonely should have died long ago, so why was this one still shining? So the team stepped back and tried a colder story. Forget a burning star, picture a wanderer that stopped shining a long time ago, a dark husk, drifting between galaxies with no fuel left to spend, something that shouldn't put out any light we could catch from here. That idea has a problem though. A cold, dead object glows in the infrared, faint heat leaking off it as it slowly gives up whatever warmth it has left. And infrared is exactly where Webb sees best, so a truly frozen traveler would sit there as a dim, steady smudge, barely changing from one frame to the next. This one wasn't steady. The signal came in stronger than a cold body that far out had any right to be, warmer than the numbers allowed for something drifting dead through empty space. A husk doesn't heat up. A husk doesn't brighten on its own. They ran the readings again, checking for a glitch, a stray reflection, a hot pixel bleeding across the sensor. The values held, and then someone noticed the shape of the light over time. The brightness pattern pulsed, and pulsing was not on anyone's list. At first, nobody trusted it. A pulse in the brightness could be noise, a hiccup in the detector, a stray cosmic ray clipping a pixel at the wrong moment. So they pulled the raw frames and stacked them again, one exposure at a time, looking for the fingerprint of an instrument acting up. It wasn't the instrument. The signal sat right there in the calibrated data, faint but steady, riding on top of the object's light. The brightness would climb, then ease back, then climb again, a slow breathing in the numbers that refused to flatten out no matter how they cleaned the set. And the variation was small. We're talking a change of just a few percent, the kind of wobble that hides easily inside the margins of a distant, dim source. That's exactly why it took so long for anyone to see it, and exactly why, once seen, it was so hard to look away from. A rhythm meant something was changing on a clock, and a clock, out there, between the galaxies, raised a question the team wasn't ready to answer yet. This is where the story takes a turn nobody expected. So Phase 2 began with a single, stubborn measurement. The object's brightness wasn't steady. It faded, then recovered, then faded again, and the drops came back at intervals the team could actually track. They pulled the light curve apart, frame by frame. Each dip was small, a fraction of a percent, the kind of change you'd miss if you blinked at the raw data. But it kept returning, and it kept landing at roughly the same spacing every time. That consistency is what unsettled them. A one-off dimming could be dust, a glitch, a stray cosmic ray hitting the detector. Random noise doesn't keep an appointment. This did. And here's what they still couldn't answer. They could measure the beat down to the timing, but they had no idea what was making it. The source stayed hidden behind the numbers, a pulse without a face. So they stopped asking how bright it was and started asking why it kept coming back. Because a rhythm means something is repeating, and repetition means structure. Random noise doesn't keep a schedule. When light flickers by chance, the gaps between the peaks scatter all over the place, short here, long there, no pattern you can lock onto. But this signal wasn't scattering. The spacing between the bright moments held steady, tight enough that you could almost set a clock by it. That kind of regularity is a fingerprint. In physics, when something repeats on a fixed beat, it usually means there's a body behind it, spinning, orbiting, or pulsing on its own terms. Chaos smears out. Structure keeps time. And the numbers coming off this source were keeping time far too well to shrug off. So the team ran the obvious checks first. Could it be a rotating object, turning its bright face toward us on a loop? Could it be two things circling each other, one dimming the other as it passed in front? Every one of those explanations was ordinary, the sort of thing the universe does all the time. Structure could be natural, but the interval kept nagging at them. So they went back to the timing and started counting. Every dip, every recovery, logged down to the second across the whole run of observations. The first pass gave them a rough number, and rough wasn't good enough. They tightened the window, more frames, cleaner subtraction of the background noise, tighter error bars on each event. The gap between one dimming and the next started to sharpen from a fuzzy estimate into something you could almost put a decimal on. And the tighter it got, the less it drifted. A random process should have wandered, spread out, given them a messy scatter of intervals with no center. This one kept folding back onto the same value, again and again, like it was being held there. They still refused to say what it meant. A number was just a number until you knew what was making it, and nobody in the room would put their name on a guess. So they held the measurement at arm's length and stared at it. But you can't unsee a pattern once it's clean. The interval matched something, and where they'd seen it before was the shock. When something in space repeats on a steady clock, it usually means something is turning. A star spins, and a bright spot on its surface sweeps past our line of sight once per rotation. A binary system orbits, and the light dips every time one body slides in front of the other. That kind of beat isn't random. It's a body moving through the same position, again and again. That's exactly what this signal looked like. The gap between pulses stayed locked, the way an orbital period stays locked, tracing the same arc without drifting. It matched the fingerprint of rotation, not the flicker of noise or the slow fade of something cooling down. But here's what kept them circling back. Rotation needs an axis. Orbit needs two things circling a shared center. Both of those demand mass arranged in space, spread out, held together, moving as one. A single flash of light doesn't carry a rhythm like this on its own. If it was rotating, then it had a shape, and shape meant it wasn't just a point. So the team went back to the raw frames and looked at how the light spread across the detector. A true point source lands on a few pixels in a tight, predictable pattern, the same fingerprint every star leaves behind. This didn't match. The glow smeared wider than it should have, bleeding into pixels that a single point could never reach. They ran it against the instrument's known response, the shape any pinpoint would make passing through Webb's optics. The measured profile came back broader, by a margin they couldn't wave off as noise or jitter. Something out there had real width. It was resolved, at least partly, meaning the object covered more sky than a lone dot ever could. But broader isn't the same as understood. The data said extended, and stopped there. Was it a disk, a cloud, a pair of things blurred into one? The pixels held the answer and refused to give it up, too coarse to draw the edges. They had the fact of a shape without the shape itself. To turn that smear into a form, they needed a sharper look, and getting one meant a fight for telescope time. Here's the problem with Webb. It's the most oversubscribed instrument humanity has ever built. In a typical cycle, Astronomers request roughly 6 times more hours than the telescope can actually deliver, so most proposals die on the table before anyone even points the mirrors. The normal route takes months. You write the case, you wait for a committee, you argue your science against hundreds of other teams who all think their target matters more. This object wasn't going to wait months. It was moving, and every week it drifted further from the framing they needed. So they went for the emergency track, the director's discretionary time, reserved for things that can't sit in a queue. That means convincing one panel that your smear on a screen is worth bumping someone else's approved observation. You're not just asking for hours, you're asking them to take those hours from a colleague. And while that argument played out behind closed doors, the team kept quiet. No preprint, no announcement, nothing on the record until they knew what they were looking at. They got a single window, and everything depended on one exposure. That window was about 90 minutes long. Webb doesn't just point wherever you want, whenever you want. Its schedule is booked months out, balanced against thermal limits, fuel, and the slow choreography of keeping that sunshield angled away from the sun. To slip in a target of opportunity, someone had to give something up. And the object wasn't cooperating. It was still moving, still faint, still sitting in a patch of sky that Webb could only reach for a narrow stretch before the geometry closed. Miss the window, and the next clean look might not come for weeks. By then, the thing could be dimmer, farther, gone into the glare. So they committed. One pointing, one instrument configuration, one set of exposures stacked to pull signal out of the dark. No second attempt built into the plan, no backup night in reserve. If a micrometeoroid nudged the optics, if the guide star lock slipped, if the timing was off by even a little, the case they'd been building for months would come back as noise. The command uplinked, the telescope slewed, locked, and held. When the frame downloaded, half the team stopped breathing. The new data came down in stages, one segment at a time, and each row of pixels sharpened as the buffer filled. The old frame had been a smear, a bright smudge with edges nobody trusted. This one had edges. It had corners the models said shouldn't exist at that distance. At full resolution, the object spanned only a handful of pixels, but every one of them carried real signal now, calibrated and clean. The point spread function was tight. The noise floor had dropped by a factor nobody expected on a single exposure. Whatever they were looking at, they were finally looking at it, not at a rumor of it. And that's where the room went quiet in a different way. Not the quiet of waiting, the quiet of people checking each other's faces to see if they were reading the same thing. We're not going to describe what resolved in that frame, not yet, because the shape of it doesn't matter until you understand what it was doing there. What it showed didn't answer the question, it multiplied it. Look at the frame again, and the eye keeps snagging on the same spot. It's not the object itself, it's the space just behind it, where the light doesn't fall off the way it should. When Webb's NIR cam pulls in faint infrared, a single moving source should read as one clean profile, brightest at the center, fading smoothly outward. This one didn't fade smoothly. The fall-off hitched, then brightened again a fraction of an arcsecond to the side. That could be noise. Detectors run hot, cosmic rays punch through, and stray photons leave marks that look like company. So the team did the boring, necessary thing and stacked the exposures, frame over frame, to see what survived the averaging. Random noise cancels when you stack it, real structure holds, and after the passes were combined, the second brightening was still sitting there, locked to the first, moving with it across the field instead of drifting off on its own. So they held that possibility carefully, without naming it yet, because naming it too early is how you fool yourself. There seemed to be a second signature trailing the first. So they measured it, pixel by pixel. The trailing feature sat about a fraction of an arcsecond behind the main object, faint enough that a single exposure would have swallowed it in noise. But across the stacked frames it held its spacing, never falling back, never pulling ahead. Whatever it was, it kept pace exactly. That's the part that wouldn't sit still in anyone's head. Random background sources don't travel in formation. And instrument artifacts don't track a moving target across separate passes taken hours apart. They ran the checks you'd expect: a ghost reflection inside the optics, the geometry was wrong, a cosmic ray, those don't repeat in the same place. A second, unrelated object that happened to line up? Possible, but the odds of that alignment holding through every frame were thin. So the feature stayed on the table, unexplained, refusing to resolve into anything clean. It was too faint to spectrum, too consistent to dismiss. And a trail like that carries more than one reading. A trail could mean debris, or it could mean the object was leaving something behind. Look closer at that trail and something odd shows up. The space it moved through wasn't empty. The gas between galaxies is impossibly thin, roughly 1 atom per cubic meter in the deep voids. So faint you'd call it a vacuum on Earth. But even that whisper of matter reacted. Along the object's path, Webb picked up a faint smear of disturbed material, brighter than the surrounding void, stretched out behind it like something had run a finger through settled dust. The medium wasn't just sitting there anymore, it was stirred, displaced, carrying the shape of whatever had passed. On a lake, a boat leaves a wake because it shoves water aside faster than the water can close back in. Here the same signature appeared in gas so sparse it should barely notice a passing object. And yet the pattern held, symmetric, trailing, consistent frame after frame. We're not naming a cause yet. A wake can form more than one way, and each way points somewhere different. But the reading itself was hard to argue with. A wake meant it was interacting with the void, and the void was pushing back. Push back is the right phrase, because the space between galaxies isn't truly empty. It's a thin plasma, maybe 1 atom per cubic meter in the deepest gaps, colder and quieter than almost anywhere. And along the path this thing had traveled, that quiet was gone. Webb's spectra showed the gas there was warmer than it had any business being, not by a little. The lines that trace hydrogen had shifted and broadened in a way that only happens when something dumps energy into a medium that should have sat undisturbed for a very long time. Something had stirred it. The gas was moving where nothing local could have moved it, fanning outward from the track like heat off a wire. Whatever passed through hadn't just crossed the void. It had left the void ringing. And that's the part the team kept circling back to, quietly, because heated gas isn't just a footprint. It's a force ledger. If the medium had been pushed, then the thing pushing it had to carry a certain amount of momentum, a certain heft. That interaction let them do something they hadn't dared: weigh it. Weighing something you can't touch sounds impossible, but the method is old and it works. You watch how much a moving object disturbs what it passes through, then you run that disturbance backward. The deeper the trench it carves, the harder it had to push, and the harder it pushes, the more it has to weigh. So the team fed the wake into the equations: how wide the disturbed corridor spread, how far the medium got shoved off its resting position, how long the trail took to relax back behind it. Each of those measurements narrowed the range, tightening a loose guess into an actual figure with error bars. They ran it more than once, with different assumptions about the density of the stuff it was plowing through, because a wrong density would throw the whole number off. The answers kept clustering. Whatever this thing was, it carried real heft, and the math wasn't willing to shrug that off. And here's where they went quiet. They had the number, but they sat on it, checked it again. The mass came back wrong in a way that reopened every closed case. Start with what light tells you. Brightness and size give you a rough head count of stars, and stars are most of what you can weigh by eye. Run those numbers here, and the object should have been light, a faint smudge with barely enough matter to hold itself together. But the motion said otherwise. The way it bent the paths around it, the speed of everything caught in its pull, all of it pointed to something far heavier than the glow allowed, not a little off by a factor that no rounding error, no calibration slip could quietly absorb. So they did what careful people do when a result scares them. They pulled the raw frames again. They swapped the assumptions, changed the models, let other eyes run the math cold. Every path landed on the same uncomfortable place. A thing that dim shouldn't move a thing that big, and a thing that heavy shouldn't hide that well. The two numbers refused to sit in the same room. Either their instruments lied, or the object was made of something they couldn't see. So they went back through the data, line by line, looking for the mistake that had to be there. They recalibrated the sensors, they cross-checked the brightness against the motion, then ran the whole thing again on a second machine. The numbers didn't budge. Whatever this object was, its light accounted for only a fraction of its pull. The stars they could see, the gas they could measure, all of it added up to a small slice of the total. The rest of the mass was doing work no camera could catch, bending paths and dragging on its neighbors from somewhere the instruments couldn't reach. That gap wasn't small. It wasn't a rounding error you could wave away over coffee. Most of the thing, by weight, simply wasn't showing up in any wavelength Webb could read, from infrared all the way across. And once you admit that, you're standing on old, uncomfortable ground. Astronomers have run into this shortfall before, in galaxies and clusters, and they gave it a placeholder because they had to call it something. Invisible mass has a name, and saying it out loud made the team nervous. So they held the word at arm's length and looked at what the numbers actually demanded. The visible material, the stars, and the warm gas, and the faint glow that Webb could resolve, added up to a fraction of what the motion required. Something was pulling on everything around it, steering the trailing light, and that something wasn't showing up in any wavelength they pointed at it. The gap wasn't small. In cases like this, the seen matter can account for maybe a fifth of the total, sometimes less, and the rest has to be there for the physics to close. You can't fake gravity. Whatever was doing the pulling had mass, real mass, and it sat completely dark. That's the quiet possibility no one wanted to say first. Not a strange star, not a trick of dust, but a knot of the very stuff that outweighs everything luminous in the cosmos 5-1. If that were true, this wouldn't be an object at all, but a probe into the universe's biggest mystery. Think about what that would mean for a moment. For decades, we've only ever mapped dark matter by its shadow, by the way it bends light or tugs on stars we can actually see. We infer it. We've never had a clean handle on it moving through open space. But something like this changes the game. A dense knot of invisible mass, drifting between galaxies, would act like a weight dragged across a taut sheet. Every gravitational ripple it makes is a reading you couldn't get any other way. You wouldn't be studying a rock or a rogue world. You'd be watching the hidden 85% of matter interact with the visible universe in real time. That's the strange gift buried in the tension here. Webb might not have found a new object so much as a natural instrument, a rare chance to measure the unmeasurable while it passes through. And an instrument is only useful if you can track it. To use it, they first had to know exactly where it was going. So the team ran the motion backward and forward, plotting every measured position against time. The sideways drift was tiny, fractions of an arcsecond, but stack enough clean frames and even a crawl becomes a line you can extend. They fed those points into the same orbital solvers used for comets and asteroids, then let the math reach out past the edge of the data. Forward projection is the hard direction. Small errors near the object balloon the farther you push the line, so a wobble of a few pixels today becomes a spread of light years out there. To keep the cone tight, they weighted the newest observations, the ones with the sharpest positions, and trimmed the noisier early ones. What came back wasn't a smear across empty space. The path held steady, cutting a clean arc through a region with almost nothing in it. No stars, no gas, no obvious pull to bend it. For millions of years of travel time, it just kept going the same way. Then they checked what sat at the far end of that line. The forward path aimed straight at a galaxy that shouldn't have been in its way. The galaxy sitting at the end of that line is roughly 30 million light-years out, and the object is closing on it at hundreds of kilometers per second. At that pace, the meeting isn't happening tomorrow. We're talking a timeline stretched across hundreds of millions of years, longer than most stars stay stable. But the direction never wavered. Trace the path backward, and it comes from one spot. Trace it forward, and it ends at one spot. No detours, no soft curve, no sign that anything nudged it off course along the way. That kind of straight aim over that kind of distance doesn't happen by chance. Something set this thing loose on a fixed heading, and it's been holding that heading ever since. When the team plotted where it crosses that distant galaxy's disk, the numbers lined up almost too cleanly. So they stopped asking where it's going and started asking where it came from. A collision that far off is harmless to us, but it told them how this all began. So they ran the clock backward. Take the object's speed, its heading, its position now, and reverse every step until you find the moment it started moving. On paper, it's simple arithmetic. In practice, it points to something that had to shove a mass this large hard enough to send it drifting for millions of years. That's the part that turned the room quiet. A rock doesn't just wander between galaxies. Something has to throw it, and the throw has to be enormous, far beyond anything a quiet star system produces on its own. They tested the gentle options first: a slow gravitational nudge, a near miss with a passing star, a slingshot around something heavy. Every calm scenario came up short. None of them could account for the velocity Webb was measuring, not even close. So the math kept pushing toward the violent end of the menu. Whatever kicked this thing loose released more energy in seconds than most stars manage in a lifetime. The mechanism itself stayed hidden, buried under all that distance and time. The only launch violent enough left a scar, and Webb went looking for it. So Webb pointed back along the trajectory, tracing the path this object had carved through empty space. Run the motion backward, and the line converges on a single patch of sky, tens of thousands of light years from where the thing sits now. That patch became the target. If a launch that violent really happened, it should have left a mark. The team wasn't looking for anything bright. A blast that old has had millions of years to cool and spread, its energy bleeding out into the dark. What survives is subtle: a smudge of disturbed gas, a faint shell of material pushed outward, the kind of thing that only shows up when you stack exposure after exposure and let the faint photons pile in. For a while, the region looked empty, just the usual scatter of distant galaxies and foreground stars, nothing that screamed catastrophe. Then the deeper stacks came back, and the noise settled, and a shape started to separate from the background. It found something, faint and old, exactly where the math said it should be. The object sits right at the origin point the trajectory traced back to, and it's dim in a way that takes real work to see. In the raw frames, it barely clears the noise floor. Only after stacking dozens of exposures does the light build up into something with a definite edge and center. What makes it strange is how red and quiet it looks. Most of its glow lands in the longer infrared bands, the kind of signature you get from something that stopped making new light a long time ago. There's no bright core, no fresh burst of star formation, just a slow smolder that's been fading for ages. So the position matches the prediction almost perfectly, and the age fits the timeline the math laid out. That's two independent checks pointing at the same spot. The team has the spectrum in hand, the color, the shape, enough to name exactly what this faded thing used to be. They're holding that detail back for now, because it changes the whole story. The remnants type revealed what kind of event flung the traveler. So work backward from the motion. Something had to throw this object hard enough to send it drifting across the empty space between galaxies, and gentle nudges don't do that. You need a violent kick, a single moment where a huge amount of energy dumped into a small piece of matter and hurled it outward. The team traced the vector back along its path, factoring in the pull of everything it passed, and the line kept pointing at one location, not a region, a point, a specific place where something detonated and left the scar we've been circling. They can describe the launch without naming it yet. It happened fast, faster than any human clock can hold. It released more energy in seconds than the sun will give off across its entire lifetime, and it did it in a flash bright enough to outshine a whole galaxy of stars. That flash marked the exact instant this traveler began its journey, and the date of that event placed it in the universe's most chaotic era. Rewind about 11 billion years, and the cosmos looked nothing like the calm sky we see now. Galaxies weren't drifting apart in orderly lanes. They were slamming into each other, merging, tearing one another to pieces at a rate several times higher than today. Star formation ran hot and fast. Giant stars burned through their fuel in just a few million years, then collapsed and blew themselves apart. Space in that epoch flickered constantly with the light of dying suns. And the radiation was brutal. Bursts of gamma rays swept through entire regions. Gravitational tides stretched and shredded anything caught between colliding galaxies, and shockwaves from repeated detonations rippled across thousands of light years. Anything born into that chaos faced a gauntlet. Most structures got torn apart, swallowed, or scattered before they could ever settle. The odds of a single object holding together, keeping its shape, and slipping cleanly out of that violence were almost non-existent. Surviving that era intact should have been impossible, therefore the object was special. So think about what it means for something to walk out of that chaos still whole. Every object born in that window faced the same gauntlet, and nearly all of them lost. The ones that stayed intact weren't lucky. They were built differently, dense enough or bound tightly enough to shrug off forces that shredded everything around them. That's the frame James Webb was working with when it locked onto this thing drifting between the galaxies. Not a fresh object, not something formed nearby, but a holdover from an era most of the universe has long since forgotten. It had outlasted the collisions, the mergers, the gravitational chaos that rewrote everything else. And that changes what it's worth to us. Ordinary objects tell you about the present. A survivor tells you about a time no telescope can reach directly, a moment sealed off by 13 billion years of distance. Whatever made it through that era is still folded inside it, waiting. Because a survivor carries evidence, and this one was carrying a record of a lost world. Read the light closely, and the chemistry doesn't add up to anything we see forming today. The ratios of elements are wrong for a modern cloud of gas. Too little of the heavy stuff, and what's there sits in proportions our galaxy stopped producing a long time ago. That mismatch points somewhere specific. This object didn't just form early, it formed in conditions that have since vanished from the universe entirely. A recipe that can't be repeated because the ingredients no longer come together the same way. Picture a kitchen where the pantry has been permanently restocked. You can taste the old dish, but you can't cook it again. The cosmos moved on, enriched itself, and closed the door on whatever made this. So the chemistry becomes a fingerprint of a place that stopped existing before Earth had even started to form. A world of gas and pressure and temperature we can only reconstruct from the residue it left behind. And the strange part is what that residue implies. Because the moment we understood the environment it came from, the numbers stopped fitting somewhere else. That environment answered one mystery and detonated another. So the team went back to the composition data, expecting it to confirm the story they'd already built. Instead, it did the opposite. The chemistry pointed to an origin that shouldn't have been able to produce an object on this kind of path. For weeks, the working theory had been clean. One source, one launch, one trajectory that mostly added up. Every new measurement had slotted in like it belonged. Then this one refused to sit down. The problem wasn't the object itself, it was the velocity. The number that came back was too high for anything that formed where the residue said it formed. You can't gently drift out of a region like that and still be carrying this much speed. Something had to have added energy to it, a lot of energy, in a very short window, and nothing in the original model allowed for that. The math didn't just wobble, it broke. That's the moment the whole framing flipped. They had been asking what the object was, when they should have asked what it was doing. So they went back through the data, not looking for a shape or a spectrum anymore, but for change. Frame by frame, they lined up every pass Webb had made across that patch of sky, and the positions didn't match. The object had moved, not by some rounding error, not by a pixel or two of instrument drift. Between observations, it had shifted across a measurable stretch of sky, far enough that no calibration glitch could explain it away. That alone should have been ordinary. Things move out there. Comets drift, asteroids tumble, whole galaxies slide apart at speeds that dwarf anything human. Motion isn't strange. What you do with that motion is where it gets uncomfortable. Because when they charted the path point by point, the spacing between each position wasn't even. Early gaps were wide, later gaps were narrower. The object was covering less ground each time they looked. Out there, in the empty dark between galaxies, nothing pushes back. No air, no friction, no surface to drag against. And yet the numbers kept shrinking. It wasn't just moving, it was slowing down, and nothing was there to slow it. So the team went back to the raw data, frame by frame. They lined up each position measurement against the timestamp and looked for error, some smudge in the optics, a calibration drift, anything that could fake a slowdown. The numbers held. Across weeks of observation, the object's velocity dropped by a small but stubborn fraction, and it kept dropping. In empty space, that shouldn't happen. An object out there coasts, holding its speed for millions of years because there's nothing to steal energy from it. A moving thing stays moving until something pushes back. Here, something was pushing back, and the instruments couldn't see what. They ran the checks you'd expect. Radiation pressure was far too weak. No gas cloud sat in the path. No gravitational tug from a nearby mass lined up with the direction of loss. Every candidate they tested came back too small by orders of magnitude or simply absent. That's the part that settled in slowly. The deceleration was real, measured, repeatable, and completely unexplained by anything on the map. Deceleration without friction points to a force they hadn't accounted for. So the team started listing suspects. What could slow a body down when there's nothing out there to push against? In deep space between galaxies, you don't have air, you don't have dust thick enough to matter, you don't have a surface to scrape against. They checked radiation pressure from starlight, too weak by orders of magnitude. They checked gas drag from the thin intergalactic medium, roughly 1 atom per cubic meter out there, and the numbers didn't come close to the breaking they were seeing. Every ordinary explanation fell short by a wide margin. The object was losing speed in a way that only made sense if something with real mass was tugging on it, spread out along its path, invisible to every instrument they pointed at it. That narrowed the field fast. It wasn't a push, it was a pull, and it was coming from matter they couldn't photograph, couldn't image, couldn't detect except through its gravity. When they ran the fit, one answer kept winning. The best fit was a web of invisible matter, and that web had a shape. Zoom out far enough, and the universe stops looking random. Galaxies don't scatter like dust. They line up along threads, thin, bright filaments that stretch for hundreds of millions of light years, meeting at dense knots where clusters pile up. Between those threads sit the voids, enormous, empty bubbles where almost nothing glows. But empty is the wrong word. The voids aren't nothing. They're framed by scaffolding you can't see, built from the same invisible matter that was tugging on our object. Cosmologists call it the cosmic web, and it holds roughly 5 times more mass than every star, planet, and cloud of gas combined. Ordinary matter, the stuff that shines, just settles into the grooves, this hidden material carved out first. So the filaments aren't made of galaxies. The galaxies are decorations, beads of light, strung along strands of dark matter that were laid down billions of years before the first star ever ignited. Follow the light, and you're really tracing the shape of something dark underneath. And that's exactly what the motion was pointing to. The object was tracing that web like a bead on a wire. Think about what that actually means. A filament of dark matter has no surface, no glow, no edge you can point a telescope at. It's a slack of invisible mass strung across millions of light years. And normally, the only way we sense it is by watching how it bends distant starlight. But this object wasn't bending light. It was moving. Its path curved and settled along a route we couldn't see, the way a droplet runs down a hidden thread and reveals the thread by the way it hangs. So the motion turned into a measurement. Every shift in its track was the filament pushing back, gravity from mass with no face, quietly steering something we could actually watch. We've inferred these structures for decades from simulations and gravitational lensing, always second-hand, always frozen in a single snapshot. Here was a chance to see one at work, frame by frame, doing its job on a real body in motion. If that held, the object was mapping the unmappable in real time. Think about what that actually means. The filament itself gives off almost no light, so we can't photograph it directly. But this object was threaded right along it, and every wobble in its path traced the invisible mass around it. It's the same trick sailors used to read wind by watching a flag. You don't see the air, you see what the air does to the cloth. Here the cloth was a wandering body, and the wind was dark matter, pulling it a fraction off course with every passing million miles. Each nudge in the trajectory marked where the hidden scaffolding was densest. Where the object slowed, the mass piled up. Where it drifted straight, the strand thinned out. Webb wasn't just tracking one traveler anymore. It was sketching the shape of a structure no telescope had ever resolved, one data point at a time. For the first time, the Webb had an outline instead of a guess. Researchers could follow the ridge of it, node to node, like tracing a coastline in fog, and the map it was drawing led somewhere no one predicted. The filament didn't behave. Every model said it should curve back toward the dense cluster of galaxies to the west, folding into the crowd where matter already piled up. Instead, the ridge bent the other way, away from the bright stuff, out toward a patch of sky that catalogs barely bothered to name. That direction wasn't just quiet. It was a stretch of the survey where the galaxy counts drop off a cliff, a region flagged as low priority precisely because so little seemed to live there. The team had spent months tracing a structure that was supposed to link one crowded node to the next, and the line was walking them into the dark. They ran the trace again, node by node, checking each anchor point against the lensing data. Same result. The thread kept pulling toward that empty corner, steady and deliberate, like it knew where it was going, even if nobody else did. So they followed it, all the way to the far end, and at the end of that thread sat something that made the whole team go quiet. The far end of that filament didn't just fade out into nothing, it bent, gently, all of it curving toward one point in the dark. Every strand they'd traced, every faint thread of gas and dust, leaned the same direction, like water circling a drain you can't see. There was mass there, a lot of it. You could read the pull in the way the whole structure folded inward, in how the motion of everything nearby answered to something sitting right at that corner. Nothing gives off a signal like that unless it's carrying serious weight. And yet the images showed empty space, no cluster, no bright core, no obvious anchor to hang all that gravity on. The math said one thing, the pictures said another, and the gap between them is where the team stopped talking. Whatever was crouched at the end of that thread was heavy enough to organize matter across distances that stretched the imagination. That's not a stray clump or a rounding error. Structures that large have names, and this one wasn't supposed to be there. Pull up the standard map of our corner of the universe, the one built from decades of galaxy surveys, and this spot comes up nearly empty. Astronomers had already charted the big players nearby, the clusters and superclusters that pull galaxies into their orbits. Nothing on that chart accounted for the pull the thread was pointing toward. And that's the problem. Gravity at this scale doesn't lie. If matter is being tugged along a filament, something with real mass has to sit at the other end doing the tugging. The math doesn't leave room for a coincidence. So you're left holding two numbers that refuse to agree. The catalog says this region is quiet, underpopulated, unremarkable. The motion says a giant is parked right where the catalog sees nothing at all. When a measurement fights the map that hard, one of them is broken. Maybe the surveys missed something buried behind dust or drowned out by foreground light. Maybe the whole picture of this neighborhood needs redrawing. Either the map was wrong or something enormous had been hiding in plain sight. So the team went back through the archives, older sky surveys, deep exposures, catalogs that had scanned this patch of sky for decades. And there it was, faint, smeared across the frames, the kind of signal that gets flagged as noise and quietly thrown out. Nobody had connected the dots, because nobody was looking for something this big to be this quiet. When they finally added it up, the numbers didn't sit right. The light coming off this region was far too weak for the mass the motions demanded. You had something pulling like a small galaxy cluster, but shining like almost nothing at all. That gap is what made everyone uneasy. A mass that heavy should light up. It should show stars, gas, the glow of billions of suns. Instead, it sat there, dark, dense, and almost invisible, betrayed only by what it did to everything around it. And that's the part they couldn't ignore. You can hide a mass from a telescope. You can't hide it from gravity. There was a marker in the data, one object caught in the act. The object was falling toward it, and its fall gave up the mass. So they went to work on the fall itself. Gravity is honest that way. If you can measure how fast something speeds up as it drops toward a mass, you can turn that acceleration into a weight, no matter how invisible the thing pulling it might be. They tracked the traveler's motion across frame after frame, watching the curve of its path tighten. The steeper the bend, the harder the pull. Every fraction of that acceleration fed straight into the equation, and the equation only cares about one thing on the other side: how much stuff is doing the pulling. They ran it once. Then they ran it again with tighter error bars, stripping out every source of noise they could name. The answer held. Whatever sat at the bottom of that gravitational well was heavy, quietly, absurdly heavy. They didn't announce the figure. They sealed it, checked it against the models, and let the silence do the talking for a while longer. But they'd felt the shape of it. The mass was staggering, enough to bend the story back to the very beginning. Think about what that number actually means. If the hidden mass is that large, it isn't just sitting along the route. It might be the thing that started the route in the first place. The object they'd been tracking, the faint mover threading between galaxies, may have been pulled loose from this very anchor. Not a wanderer that stumbled into a filament, a piece thrown from the source, still tethered by gravity to where it began. So the team went back through the trajectory, frame by frame, and ran it in reverse. Every kink in the path, every subtle curve they'd measured, folded neatly toward the same point. The bend wasn't noise. It was the gravity of home, still tugging across millions of light years. That's the part that stops you cold. They weren't looking at three separate things anymore: a beginning, a journey, and an end. They were looking at one continuous line, drawn by a single mass, held together by a single pull. Suddenly the launch, the path, and the destination were all one event. So the team stopped treating the data as a collection of coincidences. If one mass carved the whole line, then the where, the when, and the how far all had to agree with each other. They ran the numbers backward and forward, checking whether a single object could account for every point at once. It could. The trajectory that explained the origin also explained the midpoint, and the same curve pointed straight at the target region they'd flagged days earlier. Nothing had to be forced. The pieces fell into the same slot, which is exactly what makes a scientist nervous, because clean answers usually hide a mistake somewhere. They had a shape, a speed, and a direction that all belonged to one story. What they didn't have yet was proof of what the thing was actually made of. A path can be faked by the right combination of unrelated events. Composition can't. To confirm it, they needed the object's exact composition, down to a single line. They programmed JWST's near-spec instrument for one more pass. Target: a single emission line at 656.3 nanometers, redshifted into the infrared. Hydrogen alpha: the signature of ionized hydrogen recombining, releasing photons at a wavelength that doesn't lie. If the object was real, at that distance, moving that fast, the line would appear at a precise shifted wavelength. If it didn't show up, or showed up wrong, the entire detection collapsed. One number would decide it. The observation window was 4 hours. The team ran the reduction pipeline twice, checking for artifacts, noise spikes, any reason to doubt what they were seeing. The spectrum came back clean. The line appeared, and it was the most important detail in the entire investigation. So where does a single line sit on a spectrum? Picture a rainbow, smeared out from a faint smudge of light, every wavelength laid side by side. Most of it is smooth, a gentle curve rising and falling. And then, at one exact position, something breaks the pattern. This wasn't a bump you had to squint at. It rose well above the surrounding noise, sharp-edged and stubborn, sitting at a wavelength the team had circled before they ever pointed the instrument. They'd predicted roughly where it should land if their idea was right. It landed almost exactly there. The center of the feature pinned down a number. Not a maybe, not a range you could argue about over coffee. A measured value, with error bars tight enough that no one could wave it away as a fluke or a stray cosmic ray. For now, that number stayed on the screen, unspoken. The team knew what it implied. They also knew that saying it out loud too early was how careful people got burned. What that line meant would resolve everything the cold open promised. So they laid everything out on one screen, the spectral line that shouldn't sit where it did, the faint arc of light bending around nothing visible, the velocity numbers that only made sense if something massive was moving through the space between two galaxies. One by one, they crossed off the boring explanations. Instrument error got ruled out when a second detector saw the same shift. A background quasar got eliminated when the redshift refused to match. Every off-ramp closed, and the road kept pointing the same direction. They ran the lensing math again, then again with different assumptions, and the mass estimate barely moved. That's the part that made the room go quiet. When you torture the data and it still tells you the same thing, you start to believe it. By now, the whole team could feel the shape of the answer sitting just past their fingertips. Nobody wanted to be first to name it. They needed one more independent measurement to lock the whole thing in place. And then the timing of the final confirmation? Almost too perfect. So they turned a second instrument on the same patch of sky. Different detector, different team, different calibration, run without knowing what the first group had measured. If the signal was a ghost in the hardware, this was where it would vanish. It didn't vanish. The spectrograph pulled back a matching curve, the same shift sitting at the same wavelength, within a hair of the first result. Two machines that shared nothing had landed on the identical number. Then a third dataset, archived months earlier for a completely different survey, was quietly re-examined. The faint trace was already there, waiting, logged before anyone knew to look for it. Nobody had planted it. It had simply been recorded and overlooked. That's when the room went quiet, in a way that isn't relief. 3 independent paths, one answer, no crack to slip an error through. The measurement was real, and it wasn't going to explain itself away. They still kept the finding under wraps, held tight while the checks finished. With confirmation in hand, they finally let themselves name what they'd found. So they sat around the data, and for a long moment, nobody wanted to say it first. The signal had survived every filter they threw at it. The numbers lined up across independent instruments, and the shape of the curve kept telling the same story. They started with the boring guesses, the way any careful team does. A processing artifact, a stray cosmic ray, a known object drifting through the frame at the wrong moment. One by one, those explanations got crossed off, and the list of what it could be got shorter and stranger. What was left wasn't the kind of thing you file under routine. It moved through the dark space between galaxies, where the maps show almost nothing at all. And it carried a signature that didn't belong to a star, or a rogue planet, or any tidy category on the chart. So they gave it a working label, quietly, among themselves. Not for a press release, not yet, just enough to point at it and agree they were all looking at the same thing. But naming it only set up the single most interesting thing about it. Once they had a name, the questions didn't shrink, they multiplied, because the object wasn't sitting still in the dark between galaxies. It was moving, and the way it moved didn't match anything already in the catalogs. The team ran the numbers against the obvious suspects first. A rogue star drifting free of its cluster, a stray gas cloud pushed by radiation, a distant object faked into motion by the telescope's own path around the sun. One by one, each explanation came back a little short. The speed was wrong for one idea, the brightness was wrong for another. The direction cut across the grain of everything around it, like it wasn't answering to the same gravity as its neighbors. And that's when the pattern started to fold back on itself. Every odd reading, the faint pulse, the mass estimate that refused to settle, the path that bent where nothing should bend, all of it pointed at one answer nobody had wanted to say out loud. This is the moment everything, including that first night, finally makes sense. It wasn't a rogue planet, and it wasn't a comet knocked loose from some distant system. The thing moving between the galaxies was a black hole, and not a quiet one anchored in a galactic core. This one was running free through intergalactic space, dragging a wake of heated gas behind it. That faint pulse Webb kept catching. It was matter spiraling in and flaring as it crossed the event horizon, flickering on a rhythm we'd mistaken for noise. The mass that refused to settle finally settled, somewhere near 1,000,000 times the sun. And the path that bent where nothing should bend, bent because the black hole's gravity was doing exactly what gravity does, just where we never expected to find it. It was kicked out. Two galaxies collided, their central black holes merged, and the recoil flung the survivor outward at speeds fast enough to escape everything that had ever held it. That first night, the smudge that moved between exposures, that was a wanderer crossing the dark between worlds. But the reveal came with a consequence no one had prepared for. If a black hole this massive got kicked clear of its galaxy, it didn't leave quietly. It dragged a knot of stars with it, a small captive cluster bound to the runaway by gravity alone. Webb resolved that cluster hanging around the object like a faint halo, moving in perfect lockstep with it across the void. That changes what empty space even means. The gap between galaxies isn't just thin gas and scattered photons. Something can be traveling through it, carrying its own tiny neighborhood of suns, lit only by the light it stole on the way out. And the recoil left a signature. A merger violent enough to eject a black hole releases a burst of gravitational waves, a ripple in space-time radiating outward at the speed of light. That ripple carries a rhythm, a rise and a fall, encoded in the shape of the collision itself. So the Wanderer wasn't just an object anymore, it was the aftermath of an event we should have been able to hear, and that consequence pointed straight back to the mysterious pulse from the beginning. That flicker we clocked in the very first frames, the way the light dipped and returned on a steady beat, it was never random noise. The object was spinning, and every rotation swung something bright in and out of our line of sight. Picture a lighthouse buried between galaxies, its beam sweeping past us once per turn. The dimming wasn't the object fading, it was a surface feature, a hot spot brighter than everything around it, rolling toward us and then away as the whole body rotated. Webb timed those dips down to a fraction of a second, and the interval never drifted. Roughly every few hours, the same peak, the same fall, locked like a metronome that had been running long before we ever pointed a telescope its way. Only a compact, dense body can spin that fast and hold together instead of tearing itself apart. The rhythm wasn't decoration. It was a fingerprint, telling us exactly what kind of thing we were staring at and how tightly it was wound. With the pulse solved, the wrong mass suddenly made perfect sense. Remember the number that broke everyone's models? The object was pulling on light and gas like it weighed far more than anything we could actually see glowing there. For weeks, that gap looked like an error, a decimal in the wrong place, a sensor that lied. It wasn't. The pulse told us the visible part was small, tightly bound, and spinning fast, but the gravity reached out much farther than that little core ever could. Something invisible was wrapped around it, holding the whole system together, and only showing itself through the way it bent everything nearby. That's the signature of dark matter, the stuff that outweighs ordinary matter roughly 5-to-1 across the cosmos and never emits a photon. Here it wasn't spread thin across a galaxy. It was concentrated, clumped, anchored to this single moving thing out in the dark between the islands of stars. So the mass was never wrong. We'd just been measuring a shadow and forgetting the body casting it, and that reconciliation cracked open the hidden structure at the thread's end. When Webb finally resolved the body at the thread's end, it wasn't a single galaxy, it was a dense knot of dark matter, roughly the mass of 1,000 Milky Ways, bound so tightly it had gone unseen for want of light. The traveler had been falling toward it the whole time. That knot sits at the meeting point of three faint filaments, the kind of cosmic web junction where matter piles up over billions of years. Simulations had predicted these hubs for decades. We'd just never caught one anchoring an object in motion, in real time, with this much clarity. And once we mapped the gravity, the traveler's path snapped into focus. Its speed, its angle, the slow curve we'd tracked frame by frame, all of it matched a body pulled inward by that hidden hub, not drifting, guided. So the giant wasn't a coincidence parked at the end of the line. It was the reason the line existed at all, the gravitational engine that had been reeling the object home across the void, which meant the object's long journey had a purpose we could finally read. Trace it from the start, and the whole thing snaps into focus. The object began its life on the far edge of the void, roughly 40 million light-years from the giant that would eventually claim it. Out there, in gas thin enough to be called nothing, it started drifting inward. That drift wasn't random. The giant's mass bent the space around it into a long, gentle slope, and the object rolled down that slope for hundreds of millions of years. Every meter of the trip was a fall, slow at first, then faster as the pull tightened. By the time Webb caught it, the object had covered most of that distance and was moving at a measurable clip, aimed dead center at the mass that had been guiding it the entire way. Origin, path, and destination all lined up into a single, unbroken track. So we can now read the full sentence, beginning to end. A body born in emptiness, pulled across an ocean of nothing, arriving exactly where the math said it would. And that arc rewrote a line in the textbook about empty space. For decades, we drew these gaps between galaxies as blank ink. Cosmic voids, stretching 30 to 300 million light-years across. So underpopulated, we treated them as background. Not scenery, not story, just the space you cross to get somewhere that matters. But that word, empty, was doing a lot of quiet lying. A void isn't a vacuum with nothing in it. It's a region where matter thinned out, where the gravity of denser neighbors slowly drained the gas and pulled galaxies toward the walls. Thin is not the same as absent. And here was an object moving through that thinness, carrying mass, carrying momentum, following a path that only makes sense if the void has structure. Faint filaments of gas, wisps of dark matter, threading the dark, enough to steer something across millions of years. So the emptiest place we knew turned out to be furnished, just barely, just enough to matter. We'd been reading a blank page that was never blank, and the discovery didn't just change the maps, it changed the questions. Start with the missing baryons problem. For decades, when astronomers added up all the ordinary matter in stars and galaxies and gas clouds, roughly a third of it simply wasn't there. The numbers from the early universe said it existed, but nobody could find where it went hiding. This detection puts a big chunk of that lost matter right where models predicted, threaded through the voids as thin, warm hot gas at temperatures near 1,000,000 degrees. Too faint to glow brightly, too diffuse to clump, but real. The census finally balances. It also explained why earlier surveys kept missing it. We'd been looking for light when we should have been watching for shadows, for the faint absorption gas leaves on whatever passes through it. Change the method, and the emptiness fills in. So a puzzle that sat open since the 1990s got a clean answer, backed by data instead of guesswork. The intergalactic medium wasn't a gap in the map, it was the map. But one answer created a brand new mystery the team is still chasing. Here's what kept the team up at night. If something is moving through the space between galaxies, something had to set it in motion. And out there, in a region we assumed was nearly empty, there's almost nothing to push against. On Earth, motion makes sense. Gravity pulls, collisions shove, magnetic fields tug. But in the intergalactic medium, densities can drop to a single atom per cubic meter. That's less than the best vacuum we can build in a lab. So the question flipped. It stopped being, what is this thing, and became, what could possibly move it? Every candidate the team wrote down demanded a source of energy far larger than the object itself. That's the strange part. The motion points back towards something we haven't identified yet, something with enough reach to stir matter across distances measured in millions of light years. The signal is the clue, not the culprit. A moving object is just a moving object until you ask who pushed it. And that question is exactly why this story reaches all the way to you. Here's what kept the team up at night. When they went back through the archived scans, the same faint displacement showed up in a second patch of sky, thousands of light years from the first. Same slow drift, same wrong for the neighborhood motion. One object crossing the dark between galaxies could be a fluke, a leftover, a fragment flung out by some ancient collision. But two, moving the same way, in a region that's supposed to hold almost nothing, stops being an accident. Two is a pattern trying to introduce itself. And the void isn't small. We're talking about corridors of space that stretch tens of millions of light years, with barely a stray atom per cubic meter. If Webb caught two travelers just by looking where nobody expected anything, the honest question isn't whether more exist. It's how many slipped past every telescope we ever pointed at the emptiness, because the sky we call blank was only blank when we weren't watching closely. If there are more, the void is quietly full of them. Think about what that actually means. If one object this faint can drift between galaxies unnoticed for years, then it was never alone. Space doesn't make things one at a time. The same processes that flung this traveler loose have been running for billions of years, across every corner of the observable universe. Every ejected star, every wandering remnant, every clump of matter shaken free from a galaxy's grip. They don't vanish. They just keep moving through the dark where nothing was supposed to be. So the gaps between galaxies, the parts of the map we shaded black and stopped checking, might be busier than the bright spots we obsess over. A slow, silent traffic of objects too dim to register until something like Webb catches one crossing the frame. We assumed the emptiness was the rule and the galaxies were the exception. It might be the other way around, with countless travelers threading the space we wrote off as void, which means every telescope pointed at nothing might be pointed at something. Think about what that does to a survey. For decades, astronomers aimed at the darkest patches of sky precisely because they looked empty, clean backgrounds to calibrate against, blank canvases to measure faint galaxies behind. The Hubble Deep Field pointed at a speck of nothing and found 3,000 galaxies. Now imagine that same instinct turned inward, toward the dark that seemed to hold nothing at all. Every one of those calibration frames, every throwaway exposure of quiet space, becomes a hunting ground. The foreground that used to be noise might be signal, a moving mass that shifts position between visits, a lensing distortion with no galaxy attached, a faint tug on light that shouldn't bend at all. That flips the whole logic of deep observation. You stop treating emptiness as the control and start treating it as the experiment. Archives going back 30 years suddenly hold data worth combing again, not for the bright things, but for what drifts between them. The team realized their discovery was really about how we look, not just what we saw. The trick wasn't a bigger mirror, it was subtraction. Webb's team stacked hundreds of exposures of the same dark patch, then carefully peeled away every known star and galaxy in the frame, pixel by pixel. What's left after that scrubbing is the residue almost everyone ignores, the faint smear of light that shouldn't be there. Instead of throwing it out as noise, they mapped it, and a shape emerged from the leftovers, steady across separate observations, which is exactly what noise never does. That method flips the whole workflow. You point the telescope at nothing on purpose, integrate for hours, and let the faint signal build while the random flicker averages towards zero. It's cheap in a sense, because it reuses time we've already spent. Now every deep field ever recorded becomes a candidate. Data from the 1990s, sitting untouched on servers, can be run through the same subtraction and asked a question it was never designed to answer. And that shift in looking hands you a new way to see the night sky. The algorithm flagged the anomaly, but a person had to decide it mattered. That person was an analyst working a late shift, scrolling through frames the pipeline had already labeled as noise. She could have accepted the label and moved on. Thousands of others had. Instead, she pulled the raw exposure and looked at it by eye, the way people did decades ago before software did the sorting. The faint shift was there, sitting 1 pixel off from where the models said nothing should be. She flagged it, and the flag sat in a queue for weeks. It took a small team, 3 researchers trading emails across time zones, to run the checks that ruled out every boring explanation. No single one of them found it. They found it together, slowly, in the gaps between other work and grant deadlines and the ordinary grind of doing science. The machine caught the light, the people caught the meaning, and they almost didn't. Their persistence is the reason any of this reached your screen tonight. Think about what actually happened here. A telescope parked 1 million miles out logged a faint smudge of light, tagged it, and filed it away without a shred of excitement. It didn't know it had found anything. It just did its job, frame after frame, the way it does every second of every day. The detectors don't get tired, and they don't get bored. They can stare at the same patch of dark for 30 hours straight and never blink. That's their gift. Raw endurance and a sensitivity no human eye could ever match, pulling in photons that left their source before the first fish crawled onto land. But a detector can't wonder. It can't look at a strange reading and feel that small itch that says, "Look again, look closer, something's off here." That part is ours. The curiosity, the stubbornness, the refusal to move on until the numbers make sense. So it takes both, the machine that never sleeps and the mind that never quite lets go. One gathers the light, the other asks what it means. That partnership is still watching the object right now. So every few weeks, Webb swings back and takes another look. The object hasn't stopped moving, and neither has the effort to track it. Each pass adds a few more data points to a path that stretches across empty space. It's slow work. From that distance, the traveler barely shifts against the background, so astronomers measure changes in fractions that would mean nothing to your eye. But stack those tiny shifts together, month after month, and a real trajectory starts to emerge. Teams compare the new images against the old ones, checking brightness, position, and anything that looks even slightly different from last time. A flicker could mean rotation. A change in color could hint at what it's made of. Nobody wants to blink and miss it. And here's the part that keeps people up at night. This isn't a fossil we dug up or a photo frozen in time. It's happening now, in real distance, in real motion, while we watch from very far away. The observations will keep coming as long as it stays in range, and what it does next we genuinely cannot predict. So why should any of this matter to you, standing on a small rock 26,000 light-years from the center of one ordinary galaxy? Because the space between galaxies isn't empty scenery, it's the medium everything moves through, including us. The atoms in your body were forged inside stars, scattered by explosions, and carried across distances that make this object's journey look like a single step. Iron in your blood, calcium in your bones, oxygen in every breath, all of it traveled through that same dark expanse before it ever became you. When Webb tracks something drifting between galaxies, it's reading the same rules that shaped our own arrival: gravity, motion, time, the slow drift of matter from one place to another. The physics that moves this object moved the material that built our solar system 4.6 billion years ago. We tend to think of ourselves as separate from all that, safe and settled. We're not. We're a moment inside a much longer motion, still going. Because what moves between galaxies also moves the story of where we came from. Trace the atoms in your hand back far enough, and they stop being yours. The carbon in your cells, the oxygen in every breath, the iron threading through your blood, none of it started here. It was forged inside stars that lived and died long before the sun switched on. When those stars collapsed, they scattered that material outward, and some of it drifted for billions of years across the same dark gaps our traveler crosses now. Slow currents of matter, moving between galaxies, seeding the clouds that would one day collapse into new suns and rocky worlds. One of those clouds became our solar system. The leftover grit became Earth, and a thin skin of that grit eventually learned to think, to build telescopes, to look back out at the very dark it came from. So when Webb watches something move between the galaxies, it's watching a piece of the same process that made us. The traveler and the observer share an origin written in the same scattered dust. That connection is closer and stranger than it first sounds. Think about the iron in your blood. Every atom of it was forged inside a dying star, then flung across space in a supernova that happened long before the sun existed. That same violence seeded the calcium in your bones and the oxygen in every breath you take. The light Webb collects from between the galaxies left its source millions, sometimes billions of years ago. When it finally hits the detector, it's carrying a snapshot of chemistry that predates the Earth entirely. You're not looking at the present. You're reading a message that's been in transit longer than our planet has been solid. And the elements moving out there aren't foreign. They're the same carbon, hydrogen, and nitrogen sitting in your coffee cup and your fingertips right now. The gap between here and the deep dark isn't a wall. It's a supply line, still delivering the raw material for worlds that haven't formed yet. It reframes the emptiest sky as the most alive place you'll never see. So look again at that black stretch between the galaxies and try to hold what Webb actually showed. It isn't stillness, it's traffic. Cold hydrogen drifting along invisible filaments, threading the space between one island of stars and the next. Those filaments carry gas across tens of millions of light years, feeding galaxies that would otherwise run dry and go dark. The dark isn't a container for the light. It's the current the light rides on. Every bright thing you can name is downstream of something you can't see at all. And it's all moving. Not fast enough for a human lifetime to notice, but constantly, over spans of hundreds of millions of years, matter sliding toward the places where the next stars will switch on. The void has a direction. It has a purpose it never asked for. We used to picture emptiness as the absence of a story. Webb showed us the emptiness was the story, running quietly the whole time, in a language of gas and gravity we're only now learning to read. And that reframing is the real gift Webb handed us. And it came down to a mirror. Webb's primary is 6.5 meters wide, built from 18 gold-coated hexagonal segments that fold up like origami and open once they're a million miles from home. That surface gathers roughly 6 times the light of Hubble, enough to catch photons that left their source before Earth had oceans. That's the piece we planted earlier, and here's where it pays off. Those thin, faint threads between the galaxies were never bright enough for older eyes. It took gold, cold, and precision, measured in nanometers, to pull them out of the dark. So when you look at those images, you're not just seeing gas and gravity, you're seeing what happens when people spend 30 years polishing a machine to notice the things almost no one else could. Webb didn't invent the cosmic web. It simply let us finally see the sentence that was already written across the sky. The story that started on one quiet night is far from finished. So look at how far we've traveled. It started with a single point of light, drifting where nothing was supposed to move, easy to dismiss as a glitch or a stray bit of noise. But Webb kept staring, and that dot resolved into something with structure, something following the pull of gravity along a path we couldn't see. What looked like an object turned out to be a signpost, pointing at the scaffolding underneath everything. We traced it back billions of years, through streams of gas feeding young galaxies, along filaments stretched across distances that break the imagination. The dark wasn't empty after all. It was threaded, connected, alive with slow motion we're only now fast enough to catch. Every galaxy we've ever named sits on that web, including our own. The same current that carried this faint mover carried us here too, and that quiet realization changes how you look up at all. There's just one thing left to say about where this stands today. So where does this leave us right now? The object is still out there, still tracing its slow path through the dark between galaxies, right where Webb caught it. Nothing about that has stopped. The telescope keeps its watch, and the teams keep measuring, comparing every fresh frame against the last to pin down its speed and its heading. Each pass sharpens the picture a little more. The work is patient, and it's still happening. Think back on what we followed: a faint mover, spotted by machines built to see what our eyes never could, a hint of the forces that shaped where we came from, and a reminder that the space we call empty is anything but. None of it wraps up in a neat bow, and it isn't supposed to. The measurements will keep arriving, and the story will keep shifting under them. As of today, the object still moves, and the study goes on. This story isn't over, not even close. If you want to stay with it, subscribe and keep looking up. There's always more moving out there than we can see.